Shaun Cooper, as many of you are aware, was Dick Askey's final PhD student. He's now an associate professor of mathematics at Massey University in New Zealand, just around the corner from Auckland, where I got my math PhD. He read my PhD thesis, which I'm forever grateful for. In fact, it's funny, with Charles Dunkel was talking, he mentioned this yellow pad on hypergeometric functions. That's exactly what Shaun did with me. I studied on my own, but then I got the real education about it. And so that was really a turning point for me in many ways. He's an expert on Ramanujan and elliptic functions, and is really fantastic. So I guess Shaun, now if you'd like to speak, that'd be great.
Okay, so hello everyone, and to the organizers. I'm just so happy to be part of this celebration of Dick Askey's life. Just over 30 years ago, I was a graduate student, and there was a notice on the notice board for a special functions seminar, Thursday at 12 noon. I was a new PhD student, fresh from New Zealand. This was before the internet. I was completely naive, didn't know anything. Heard about de Brange's proof of the Bieberbach conjecture, and that Askey had been involved in some aspect of the proof, but didn't know any details. I certainly had not heard of the Askey-Wilson polynomials or Askey-Wilson anything for that matter. I did have Rainville's book on special functions, which, if I'm honest, struck me as useful to know, but not something that you would read from cover to cover. And so I was intrigued how a seminar could be run on such a topic, so I went along. So in that first seminar, Askey saw that I was new. He asked my name, said welcome, and I felt very welcome, and I was just one of the group from then onwards. The other participants, the regular ones, were Warren Johnson and Ranjan Roy, who would drive up from Beloit College every Thursday. And I learned much later that, of course, they were writing a book. The topic that semester was Selberg and Chowler's paper, Epstein's zeta function. That's what it is. The sum's over, it's a double sum over all integers m and n, except for the infinite term, which is omitted. A and C are positive, and B is real, making the 4ac minus b squared is positive. And the real part of S is greater than 1 for convergence. Often with these seminars, Dick would give us notes written on ditto paper. And, this one is, you can see the notes have just lasted a little bit better than the paperclip at the top of the page there. And I'm pretty sure if you put your nose close to the screen, you can smell the knitted spirits still on the paper. But what's happening here is that, that the title, Selberg-Chowler on the Epstein zeta function. So Dick starts with the Riemann zeta function, and he needs to get the analytic continuation. So you can see these beautiful handwritten notes, written with sections. The equations are numbered, and nice, clear, crisp sentences. There's a theorem down there, the functional equation, and then Dick gives a proof. So he does it by Poisson summation. I'm jumping a few pages. We're on page 5 now, and he does your Poisson summation formula and getting the transformation for theta functions, and then getting the functional equation for the zeta function. Then he starts, so down the bottom of the page there, Selberg and Chowler considered a two-dimensional zeta function, and just enough words to really precisely and clearly just say what's going on. A couple of pages later, so we're on page 7, and in the middle of the page here, he's got another representation for that function in terms of what zeta functions and gamma functions and a sum of Bessel functions. And this came just like that. He would do all these calculations on the board, and I was just mesmerized. I was had never seen anything like that before. Here's one of my favorite photos of Dick, and just some observations about him. You can just tell from the stance. He's got the energy, and here's a word which I hope I can use: poise of an athlete. You can just see that there. The blackboard skills are just masterful. Just the precise way that he's used that just small amount of space. In his left hand, because he wrote with his left hand, as a piece of chalk, and also in his shirt pocket, he always had, I don't know what he had in there. I think his glasses and some pens and things. And look, he's all business. No messing around. It was thrilling to watch him give a talk. And that's what his seminars were like. So the special functions seminar ran every semester that I was there in Wisconsin. And Askey also he often taught a graduate course on special functions, which met 3 hours a week, and much the same style, but with a slightly slower pace that was more humanly possible to keep up with. So what I observed, every week, I mean, I hope I learned some of it, was how to think about formulas, the things you don't learn in textbooks. So often Dick would get a formula, and then he would say, look at this parameter. When A is 1 on the right-hand side, you get a pole or something like that. You should be able to see the pole on the other side of the formula. And he would have all these checks, and he knew all these formulas personally, and had all these ways of just checking that they made sense, and that they that what you had written down, all the factors were in the right place. Look, every week I received master classes from Dick on how to teach and how to give a mathematical talk. It was, like I said, it was thrilling, just being there. And the notes that he gave were just beautiful, and really direct and to the point.
اساسا يعني اسم مبرهس كل واحد النهارده بيتكلم على
I think someone's got their microphone on.
السيريز
So
بتاعته.
we never went back to the Epstein zeta function after that. And as far as I know, Dick didn't write any papers on that topic. And I'm still curious today as to why we were even studying that paper that semester. But for me, it didn't matter. I was thrilled, instantly hooked, and that was my introduction to special functions. And I knew that I wanted to do more of whatever that was. So this was 1990. So for 30 years or so, Epstein's zeta function just remained a happy memory for me until a couple of years ago, when a colleague of mine at Massey University here from the chemistry department told me about some work he was doing on lattice sums from chemistry. And I'll say something about that hopefully at the end of this talk. So I just want to say something about the Macdonald identities and something about Morris. This is what Dick always called a theta product. Basically, it's the simplest function that you can write down. It vanishes on a bilateral geometric progression. The first set of factors in this infinite product, if you just write down where the zeros are, that's got zeros at these negative powers of q. The next factor in the product, that's got zeros at the positive powers of q. And then there's this x equals 1. This is slightly asymmetric, so I've just popped that out in front on its own. So that's called a theta product. So by Laurent theorem or something or other, that'll have a Laurent expansion in powers of x. And it's pretty easy to just replace x with qx. That just shifts some of these factors up or down by 1 and divide one by the other. A functional equation that implies a recurrence relation for the coefficients, and you can pretty much solve that recurrence relation up to the constant term c0, and then you just need to find that last coefficient c0. So I'll skip those details. when you work it out, the C naught of Q, the best place to put it is on the left-hand side. It turns out to be an infinite product, and the result is called Jacobi's triple product identity. So again, the way to view this is it's the Laurent expansion of the simplest thing you could write down that has zeros on a bilateral geometric progression. So the Macdonald identities are what happens, or what you get, when you try and do this in several variables. So we're going to generalize the X that's here into several variables. So to do that, you need some structure, and that's provided by what's called affine root systems, which in turn come from the classification of affine Lie algebras. So rather than go into all that, I just want to just briefly put up an example. So this is the affine root system for G2, and you'll just notice there's like a hexagonal diagram, and there's this vector alpha indicated here, and the slightly longer vector beta out in that direction. So pay attention to those two vectors, and also these little red dots. There's one there, another one there, and this one at the top. So there's something called the short roots. So that's alpha, this one we've got, and these other equidistant red dots. So that'll be alpha plus beta, and this one will be 2 alpha plus beta. And they're the long roots. So the long roots are beta, this one over to the right, which would be 3 alpha plus beta, and this one at the top, 3 alpha plus 2 beta. So again, I'm not really giving any details. This is really, really brief. Formally exponentiate them. So X is e to the alpha, Y is e to the beta, and then you cook up, you put a theta product for each of the roots. So the short roots, alpha becomes X, alpha plus beta becomes X, Y, and so on. So the short roots, you put a theta product on a power of Q. The long roots, you put another theta product for each one on a different power of Q. And the objective is to expand all this as a Laurent series in 2 variables. That's the objective, and you want to find the coefficients. Of course, if you just use Jacobi's triple product, you would get a series for each product. That gives you 6 sums. We want to write it as a double sum. So there's the question again. And when all these powers of Q, when it's just Q, that's called the Macdonald identity for G2. And the other interest is when the long roots are on base Q cubed. That's called the Macdonald identity for the dual of G2. So they're the cases of interest. And it's pretty easy to get using functional equations to get recurrence relations. And then the question boils down to finding the constant term. So Askey knew what the constant term was for the Macdonald case, and he knew what it was for the cubic case, and his question was, what happens when the long roots are on base Q squared? What's the constant term? And he said to me that the obvious answer, now what's that? The obvious answer is to just look at the example here and say, well, maybe it's just replace this 3J with 2J. That's the obvious guess. And so Dick knew that was wrong. That's not the answer. And his question was, what is the constant term? Look, so I solved this problem, and basically how I did it is the first 3 factors can be expanded as a double sum using what's called the A2 identity. And the 3 products involving the long roots can also be expanded as a double sum. That gives a quadruple sum for the whole function. And then when you extract a particular coefficient, that turns out to be a double sum. And then miraculously, that double sum can be converted into a product by the A2 identity. And there's the answer to the question. Yeah, there's a few more details than that, but that's the essence of the idea. So when you specialize S and T equals 1, you get the answer that Askey already knew. When S is 1 and T is 3, you get the answer. And then there's the answer to his question. To complete the series expansion, you also needed to know a second coefficient, and that's when these other factors on base q to the 5 arise. So look, how did Askey know what the answer was in these two cases, but not in the case that he asked the question about? Some things called constant identities for truncations of these infinite products. And these had been thoroughly investigated by one of Askey's earlier students, Chip Morris. And Askey always used to say about Morris's thesis that it was worth 10 PhD theses. I just took that comment at face value, that it was an impressive thesis. I mean, it's also a little bit intimidating. I mean, maybe I was supposed to write 11 PhD theses to impress him or something. But look, Askey was just genuinely impressed with Morris's thesis. Askey was also proud that, and he said this a few times, that you may wonder what happened to him. Morris didn't write any mathematical papers. He went on to have a successful career in dance choreography, and Askey was very proud of that. And I never met him, but if you Google Chip Morris dance, you can find him, and you can see his picture and what he's up to and all that. Still working in the dance industry. If you get a Fox News reporter, that I think that's the wrong guy. Anyway, so that's Morris. The list of students. So Morris was number 10. Dennis, you're there. Warren is there. I roughly know what happened to about half of these people. The other half, I don't know anything about. So after I got this, I had a chat with Dick. I said, what do we do with this? So we've answered the question. He said he didn't know, but he was convinced there must be more to do with it. And he guessed it might have something to do with cubic transformations for hypergeometric functions. Look, I still don't know to this day what to do with it. But I did get 2 other things from it. So I'd like to just briefly talk about those for a sec. After I tried looking at these Macdonald identities, by the way, 2 variables was about as far as I got. N variables was too many for me. I went back to 1 variable and just asked, what are the Macdonald identities in 1 variable? And one of them is the Jacobi's triple product identity. The other is the quintuple product identity. And here it is in Gasper and Raman's book. And look, all of the tricks that Dick taught me about how to view a formula, how to look at its structure, how to see what it means, none of them really seemed to work on this one. And I was just baffled by it. And to be honest, when I see this formula, it's easy to prove that's not the issue, but why is it like that? I mean, you can look at the zeros on the right-hand side. It didn't really seem to give me any clue. Look on the left-hand side, and look, my heart just sinks a little bit. I just don't get why that series should be considered. So it troubled me, this identity. Here it is in Ramanujan's notebook. So this is maybe a little bit better. And now that I know a little bit about what Ramanujan used this for, I can kind of get it, but still it doesn't sell itself to me. I couldn't give a convincing talk onto why this, why it should be written like that. And again, as I've just said, it's also the Macdonald identity for the affine root system BC1. So I just didn't get it, and it troubled me. So I decided I would read every paper that there was on the quintuple product identity and study every proof, and hopefully after that I would be enlightened. So that was my idea. IJNT, that's not my personality type or anything like that. That's a journal, International Journal of Number Theory. That's where I wrote this stuff. So here's my two favorite descriptions of the quintuple product identity. So Jacobi's triple product in its symmetrized form provides a factorization of this series. It's got a quadratic exponent on the Q and a linear exponent in X. The quintuple product identity, by analogy, provides a factorization of basically the same terms, except you weight them with a 1, a -1, or a 0, according to the residue class of the J modulo 3. So that's a very simple-minded way of looking at it, but I like simple-minded, and this is one that I can remember. So that's one of my favorite ways of looking at the quintuple product identity. Another way, which I'm going to be sort of deliberately vague about, is the product side of Jacobi's triple product identity can be made to specialize to the sine function when Q is 0. And in the same way, so what I'm trying to get at is the quintuple product identity is to the triple product identity sort of what the cosine is to the sine. So again, this is deliberately vague, but if you see what I'm talking about, I'm hoping you'll sort of agree with that. And here's a reference if you'd like to look that up. Anyway, so I'm now much happier with the quintuple product identity, and that came out of that. Look, here's another consequence of the G2 Macdonald identity. Here's Jacobi's triple product again. If you remove this 1 minus x factor by just dividing it onto the other side, and then put x equals 1, then the three factors turn out to be the same, and you just get 1 minus q, the same factor, 3 times. To take the limit on the right-hand side with the series, you need to combine the terms in a particular way and take a limit. But if you do all that, this is the result that you get. And look, why is this q to the 1/8 there? Look, it's just there because the quadratic exponent, if you complete the square, it's just what you get. It just creates a 1/8. And so you just put that on the other side. And when you see this series, you see this, you could view this as a sum over the integers, which are 1 mod 4. So that's just another way of writing that. So this is well known. I think Jacobi knew this. If you do the same thing on the Macdonald identity for G2, so this time there are 6 factors that you need to divide by first. And then there are 2 variables to let go to 1. Then if you basically do the same process, you end up with the 14th power of what's called Euler's product. And instead of just a single factor alpha, you get basically 6 factors down here and a quadratic power of q like the quadratic power up there. And the sum is just over certain integers alpha and beta, just like the one up there. So Macdonald knew this 50 years ago in his 1972 paper. And just, so there it is again. If you just remove the fractional power from both sides and consider the product, then this has the corollary that almost all of the coefficients in the expansion are 0. So that's because the exponent here is a quadratic form in just 2 variables. And of course, what that means is just look at the coefficients up to some value, capital N, count how many of them are non-zero, divide that by the number of coefficients, that goes to 0 in the limit. And look, it's a theorem that if you consider even powers of this product, then almost all of the coefficients are 0 if and only if the exponent is 2, 4, 6, 8, 10, 14. That's the one we're talking about, or 26. So that's a theorem. of SEER. Just incidentally, last time I checked for odd values of D, that's the answer is unknown. Well, what is known is for the first power and third power. You get those by the triple product identity. Almost all the coefficients are 0, but nothing has been proved for other odd values of D. And just by contrast, for the 24th power, that's where the Ramanujan tau function comes up. The absolute opposite is conjectured to occur. The conjecture is that none of the coefficients are 0. And again, as far as I know, that's still a conjecture. So anyway, 10 or 12 years later, I had the enormous thrill of working with Henghua Chan and Pichun To. And what we were able to do is so these factors here you recognize from the previous formula, we've powered them up. So there's now a power of, I think these might be the short roots raised to the power of m. These come from the long roots raised to another power n. It's the same quadratic exponent. So we're summing the same terms, just with different weights. So m, n, and l are integers. And what we found is that this series is basically the 14th power of Dedekind's eta function again, times a polynomial, some things called P, Q, and R. They're called Ramanujan's Eisenstein series. And it's a polynomial. We've got you can say what its degree is. This was just an incredible result. And like I said, I was really thrilled to be involved in this work. And we got similar results for the other powers up to 26. So this problem that Askey set me all those years ago gave me access to working with these guys and getting this result. Another time in the seminar, one day, Askey showed up and this technical report out of India had come out. Askey had photocopied the whole thing and plonked a copy down in front of me and said, "Why don't you edit this?" I think that was the instructions. And I just said, sure. And in the seminar that day, Askey started working through the first chapter of this book just to help start things off. What was in there? So these are these Eisenstein series we just saw on the previous page, P, Q, and R. They satisfy these non-linear differential equations. And so this book, just within just a few pages from scratch with full details, these results came out. And again, I was just thrilled beyond measure when I saw this. I just couldn't believe it. And moreover, q cubed minus r squared. These are just this is incredible results. Have this factorization. So I had 3 fairly good attempts at editing the manuscript as Dick asked. So during my thesis, I worked, more or less through the whole thing, but I was, I hit some blocks that I just couldn't overcome. Also, I wasn't quite sure how this was going to help me get a thesis, editing somebody else's work. I didn't know if that would really count for a thesis, so I ended up putting it aside. I had another go a few years later when I was on sabbatical, and then finally it was going to be the centenary of the author's birth, and so I decided to sort of finish it off. What I needed was I needed to understand more of Bruce Byrne's work, which had been on Ramanujan's notebooks, which he'd been doing all this while, and I also needed access to and to understand work of Henghua Chan to fully understand the manuscript. Anyway, I'm happy to say that it got finished and published, and there's a picture of Dick with Henghua Chan, and Dick is holding it's the most overdue homework assignment that I've ever had. This one was 20 years overdue, and I think Dick was happy when I finally handed that in to him. Clausen's identity is something that very much interested Dick. And here's a page from his graduate course notes. So, and this is interesting just to see how he goes about it. So Dick just starts with a 2f1 hypergeometric series and decides to square it and just says, let's see what happens. So he writes out the first 3 terms. And okay, 1 is trivial, the x term is trivial, and then the quadratic term starts to get messy. And so he says the question, if this is to be a hypergeometric series, it's got a factor. And so he looks at the term and says, well, how could this factor? And he tries the first thing that you might think of. It doesn't seem to work. So he tries something else, and he just goes for it and sort of makes an assumption, and he just like that, the second term, just by accessing the quadratic term, goes like that, and just like that, he's guessing Clausen's formula for the square of a 2f1. And the notes just carry on. So again, just beautiful how to think about how you might discover something like that. And then once you've got it, you can prove it by differential equations. Skipping a few pages ahead here, and Dick mentions that for a few years, Gregory Chudnovsky asked Dick to find an extension of Clausen's formula. So this was something that Dick was interested in and tried himself to get an extension. And again, I'm skipping forward on these notes a bit further, but here's something very, very modest. He says, here is one comment on Clausen's formula and proof of the Bieberbach conjecture. De Brange needed to prove such and such. And he goes into it. He says it's not actually Clausen's formula, it's something else. And he says what it is. On the next page, look, it's just a page and a half. And he gets this formula. He said, clearly this is positive. And de Brange needed this for these values. And this is what the famous positivity result that was needed in the proof. And very modestly, Dick says this proof was found by George Gasper. It's a nice use of the non-negativity in Clausen's formula. So just a page and a half, quite incredible this just in the class notes that we used to get. Here's a generalization of Clausen's identity that Dick would have been very interested in. So, and I would just take a moment just to look at it. So we're going to consider this 3-term recurrence relation. If you like, it's a generalization of Fibonacci numbers, if you want, that the next term depends on the 2 previous ones. Instead of just simple addition, the coefficients are polynomials of degree 2. Then you form the generating function for this sequence and square it like you do for Clausen's identity. And that can be given as a single power series involving the same coefficients. Centralized binomial coefficient, you can write that in terms of 1/2 sub n over n factorial. This is what kicks the series up from a 2f1. This kicks it up with it, putting in an extra parameter to make it up to like a 3f2. And we get this, this change of variable that's there. If gamma is 0, this is easier to understand. If gamma is 0, the 3-term recurrence relation becomes 2 terms. And the series on the left-hand side is actually a 2f1 hypergeometric series. And when gamma is 0, this right-hand side, this power series variable becomes just x1 minus alpha x. It's like a quadratic transformation. So this is a 3f2 function with x1 minus x as the power series variable. So that's something we can all understand. And this identity was found by 4 authors. And the way they found it, I mean, how does one find a result like this? You don't just get out of bed one morning and write this down. They essentially discovered 3 special cases for particular alpha, beta, and gamma, parameterized by modular forms of level 6. And then they just extrapolated the general result from that.
Excuse me, Shaun, something, why there is no beta on the right-hand side? What happened to the kind of mysterious?
Yep, that's absolutely correct. There's no beta. That's the question. I think if you write down the differential equations that are satisfied, the beta will come back. But yeah, that's a good observation. There's no beta there. Yep.
Buried in the Tn on the right side.
Yeah, exactly. Here's another one. Let's see if there's a beta in this one. There's a second generalization of Clausen's identity. So this 3-term recurrence relation for the t's is the same as we had. Here's another 3-term recurrence relation involving s's. This time, the coefficients are polynomials of degree 3. And yeah, I should point out that you just need one initial condition to start the recurrence, because if you put n equals 0 in either recurrence relation, the tn minus 1 term, the coefficient will be 0 because of the n squared or the n cubed. So you just need one initial condition to get started. Anyway, here's the Clausen type formula. Again, there's no beta in the power series, but it's in the coefficients there. So there's a second analog of Clausen's identity. And I'll just point out that when, for this particular parameter set, you get the SNs are what are called the a priori numbers, which a priori famously used in the irrationality proof. So, Dick knew to look for generalizations of Clausen's identity, and again, just stunning results here. Look, I need to sort of wrap up soon, so I just wanted to go back to that first seminar that I attended as a student. So just want to mention really briefly some work that, so Peter is a colleague of mine. He's a chemistry professor here at Massey University, and Anthony is a PhD student. And so they were interested in, you go back to high school chemistry and packing of atoms. This is the hexagonal close packing structure. And so we're going to refer to some parameters A and C. A is just the length of one of these hexagonal sides, and C is going to be the height between two of these layers of hexagons. When the ratio C over A is √8/3, that's the hexagonal close packing arrangement with 12 kissing spheres around a central atom. I never knew this, but there's something called the Leonard-Jones potential. Using an inverse power law. What are all these things? All you need to know is that R it's a function of R, which is the distance between two atoms. The other parameters, R, E, and epsilon, you can set those to 1 if you want. And these powers, M and N, so they're often taken to be 12 and 6. And this is what I didn't know. I thought everything in physics was inverse square laws. That was what I assumed. I always thought the inverse power, use a second power. But apparently, my chemistry knowledge is 100 years out of date, at least. The powers 12 and 6 fit well with experimental data, is what Peter tells me. And to estimate what's called the cohesive energy for the whole lattice structure, what you need to do is take this potential and insert these sums over the whole lattice, where for the hexagonal close packing structure, the lattice sum is So this I squared plus ij plus j squared, that comes from the hexagon. The gamma squared k squared, that comes from the different levels of the hexagons. And then there was that other intermediate layer, which is sort of shifted over. So ij are shifted by a third, and because it's half a level up, the k is shifted by a half. So the chemists are interested in evaluating these sums. And so again, so the prime on the sum just means the I, J, K all being zero term is omitted. What do you do when faced with this? So of course, I just dig out Askey's notes from that first seminar, look up what he did and just adapt it to this situation. And what you end up doing is you end up getting some functions that I was by now very familiar with working with, the cubic theta functions. And what you need is just some simple properties, their modular transformation properties, the number of solutions in integers of a couple of things, and K-Bessel functions and some analytical skill. What did we find? So, I won't go into the details, except to say that we've considered like a one parameter family linking body-centered cubic to face-centered cubic. We're interested in why some structures are more stable than others. And, some of the calculations we've done have some implication potential, whether the underlying assumptions are valid or not. And back to the hexagonal close packing one. So this paper is almost ready. It'll be on the archive hopefully in another month. Basically, these minimums here, one of these is the 12,6, this black line at the top. This black line, this is the gamma equals √8/3. So many crystals physically exist in the hexagonal close packing structure. There is the second sort of metastable state, which is around about the 2/3 ratio, and that has some physical significance, and there are some, this is observed in what are called hard potentials and disappears in the soft potentials. So yeah, look, this was an unexpected, again, another thrill for me, just that I've got access to the skills to be able to do this. I was just reminded of Askey's warning not to study special functions just in isolation, or you risk becoming quickly sterile. Askey was always interested in how special functions arise in other situations. I'm pretty sure he would have gotten a little kick from seeing this. And look, for me, I could not have thought about asking the questions about lattice sums that the chemist did, but at the same time, I was able to prove some theorems that they weren't able to. Look, here's the last slide. This talk could easily have been 10 times as long with 10 times as many topics. Askey used to say, when a mathematician dies, a lot of knowledge is lost with them. And while that's certainly true of Askey, it's also true that he left us with so much. Okay, look, my time studying in Wisconsin with Askey, look, it set me up for my whole career, and in all sorts of ways. It's what I learned studying with Dick, the stuff I learned, the example he set, really influenced me profoundly. He helped me enter a paradise of mathematics and to help me find my way around it a little bit. I'll forever be grateful to Dick for that. And that's the end. Thank you for your attention.
Any questions? I had a quick question. Could you comment a little bit on formulas like Clausen's formula for Q hypergeometric functions?
Clausen for So there is a Q analog for sure. And one of the things that I've got no idea on how to start would be how to find a Q analog of this one here. I've got no idea how to do that. What's a Q analog of this rational function on the right-hand side? No idea. Is there a Q analog of this 3-term recurrence relation? For 2 terms, yeah, you can just make it into, you just replace the integers or the real numbers with their Q analogs, and you can do that. So that's a great open question. I've got no idea whether a Q analog of this exists or not, or of the, where's the other one? Or of this other one. I've got no clue.
Anyone else have any other questions?
I want to make a remark.
Sure, go ahead.
I think as far as I know, Shaun is the first person who has presented our joint work on the lacunary series. I think Shaun can you go back to this one. Yeah, he's the first who actually presented this work for the first time. The reason is, I think, because although the 3 of us were doing all this work, I think none of us remember how to do all this work or how this work was done eventually. So that's my remark.
Yeah, thanks, Hengpart. To be honest, I was a little bit afraid that someone might ask some questions about this and I might not be able to answer them. But it was a thrilling project, and I'm pretty sure there's more work that can be done there. So, for example, we did not do anything on this. Where is it? So there's this dual case when the case we did was when all of the roots are on base Q. There's also the case when S is 1 and T is 3. The dual case, and we didn't consider that, and so there, I'm sure there's other. What we did could be extended to that case as well.
Other comments or questions?
Can you do what you did for G2, decomposing into 2 A2s for F4?
That's a great question, Dennis. I tried really hard to do that, and I couldn't get it to work. It's the correct number of factors, and I really wanted to make it happen. It's almost a miracle that works in this G2 situation. But this question you asked, I tried pretty hard for quite a while to do that, and I didn't succeed. So I'll just answer by saying I couldn't do it.
I have a question. So when you came to medicine from New Zealand to graduate school, you didn't yet have in mind a specific professor to work with. You just went to seminars and so, and then picked the professor you liked. Was that the case?
Hi, Tom. Yeah. Look, I had no idea what I wanted to do. And like I said, I really was naive. I didn't know what mathematical research was or anything. And one of the reasons I chose Madison, Wisconsin was because it was one of the biggest departments in the United States. And I thought, the probability of finding something I like, something I was interested in, must be high by going there. I mean, I'd heard of Rudin, but both Rudins actually, and I'd heard of Buck, and I've heard of Askey. And I, didn't know what I wanted to do, but after that, one seminar in Askey's, I knew that's what I was going to do. Yeah. It's as simple as that.
And about Morris, who has gone into dancing, I think Dick Askey may have liked this because he has always liked going to dance performances. If you read the Indian diary, so they had many performances there, and they they always liked it very much. Probably also with more classical dance, classical Western dance, Russian dance, and so he maybe have been fond of Morris going that way.
Yes, I know Askey used to go to the Wisconsin Players Theater. I think it was what it was called in Madison. He was a big supporter of that as well. Yeah, he liked the arts for sure.
Well, let's thank Shaun